Welcome to the Physics Classroom's video tutorial on light and color. The topic of this video is Young's experiment, and we want to know what is Young's equation and how is it used, and how do you perform Young's experiment. I'm Mr. H. Let's get started. In a previous video, this one, I discussed two-point source interference patterns. It's somewhat of a precursor to this video, so I've left a link to it in the description section if you need to review it. A two-point source interference pattern consists of nodal and antinodal points that lie along lines. The antinodal points result when waves from one source constructively interfere with waves from the other source. The nodal points result when waves from one source destructively interfere and cancel out the effect of waves from the other source. If this collection of antinodal and nodal lines are projected onto a screen, you'll see a series of alternating dark and bright bands on the screen. Wherever an antinodal line lands up on the screen, you'll see a bright spot, sometimes called a maximum, because light from one source is constructively interfering with light from the other source to produce a point of maximum intensity. Wherever the nodal lines land up on the screen, you'll see a dark spot, because light from one of the sources is destructively interfering and canceling out the effect of light from the other source. This collection of dark and bright bands can be analyzed, measurements can be made, and the wavelength of light can be determined. The experiment that I've just roughly described is known as Young's experiment and was first performed by Thomas Young in the year 1801. Young's equation relates the measurable quantities of Young's experiment to the wavelength of light. I won't be deriving Young's equation in this video, but if you need to see it, it can be found on our website. It's found in many college physics textbooks and is quite complicated. I've left a link to this derivation in the description section if you need to review it. Now, in Young's experiment, monochromatic light from a laser is shined upon two narrowly spaced slits. The light diffracts through the slits and is then projected onto a screen some distance away, forming alternating bright and dark bands on the screen. In order to determine the wavelength, you'll need to measure four quantities. First, the distance between those slits, known as d. Second, the distance from the slits to the screen, known as L. Third, the distance between bright bands or dark bands on the screen, that's y. And finally, the value of m for the particular band that you've selected. Young's equation looks like this. The wavelength, lambda, is equal to y times d divided by m divided by L. In order for this equation to be valid, four things must be true. First, the light must be monochromatic. Using a laser ensures that. The sources must be coherent, producing crests at the same time as one another and producing troughs at the same time as one another. And by shining a laser light up on two slits to form the two sources, that ensures that the sources are coherent. Third, the distance L must be much greater than the distance y. And finally, the separation distance between the slits must be much greater than the wavelength of light. The two most common difficulties students have with performing Young's experiment are first, units, and second, understanding what the variables of Young's equation represents. Let's begin by talking about those variables. First, the lambda in the equation is what you're trying to determine. It refers to the wavelength of light. Second, the value of y and the value of m is something you'll be measuring or determining when you look at the screen where those bright bands are located. The value d is the separation distance between slits. It's measured on the slide, but in actuality, usually the manufacturer of the slide provides the value of d. The value of L is measured from where the slide with the slits is to where the screen is. Let's talk a little bit more about y and m. Here's a magnified view of the screen with its alternating dark and bright bands, the bright bands being called maxima. You'll notice that the bright bands are equally spaced apart, and the value of y and m will go together. In fact, the ratio of y per m simply gives you the distance between two immediately adjacent bands. what I recommend you do is measure the distance between two bands that are pretty far apart. For example, consider this situation here. I'm measuring the distance between the second maximum on the left side of central to the second maximum on the right side of central. Now, that's measuring 4 spacings between bands. M is equal to 4, and Y is whatever I measure. Here's another way to look at this. Since bands are equally spaced on the screen, measuring from the second maximum on the left to the second maximum on the right is equivalent to measuring from the central maximum out to the 4th antinodal line or 4th maximum on either the left or right. So the M value of that 4th maximum is 4, and the Y value is the distance from the central one to the 4th maximum, equivalent to the distance from the second maximum left side and second maximum right side. Since it is a common student difficulty, let's think a little bit more about the meaning of the variables in Young's equation, but instead of doing it with a Young's experiment setup, let's do it with verbal statements. I have 3 examples, and here's the first one. We'll read through and identify the values of Y, D, M, and L when we come to them. 2 slits are separated by 0.25 millimeters. That's the distance between slits. That's D in Young's equation. Produces an interference pattern in which the 5th dark band is located 12.8 centimeters from the central antinodal line. So the 12.8 is the value of Y measured on the screen where the bands are. And it's measured between the central maximum, the central antinode, and the 5th nodal line. And so if you think how far away that is, that's 4.5 full spacings away. The 5th nodal line is between the 4th antinode and the 5th antinode, giving us an M value of 4.5. And it says when the screen is placed 8.2 meters away from the slide, so L is 8.2 meters. Now in our second example, 2 sources are separated by 0.500 millimeters. That's the distance between slits or sources. That's the D value. Produces an interference pattern 525 centimeters away. That 525 centimeters, how far the screen is from the sources. That's L. The 5th and the 2nd antinodal line on the same side of the pattern are separated by 98 millimeters. So the 98 millimeters is Y. We need to determine the M value, often the most difficult part. So if you think the 5th and the 2nd nodal line, you can do some counting there. So 2nd, 3rd, 4th, 5th, that's 4 bands on the screen, and the number of spaces between 4 bands is 3. So M is equal to 3. In our last example, probably the most difficult one for the value of M, it says the 5th antinodal line and the 2nd nodal line on opposite sides of the pattern are separated by 32.1 centimeters. So that's a Y value, 32.1 centimeters. The M value here is 6.5. So the way I can think of it is I want to know the M associated with the distance from the 5th antinodal to the 2nd nodal opposite side of central. So from central to the 5th antinodal is 5 spacings. And then from the central antinodal to the 2nd nodal opposite side is 1.5 spacings. That 2nd nodal is between the 1st antinodal and the 2nd nodal, which is why you get 1.5 there. So that becomes 6.5 for M. When the slits are 6.5 meters from the screen, so 6.5 is the distance from slits to screen, that's L. And finally, the slits are separated by 25.0 micrometers. That's the value of D, 25.0 micrometers, and that's how you write the symbol for it. Young's experiment today is performed with laser light, and the goal is to determine the wavelength lambda of the laser. The double slit is usually provided by the manufacturer, so the distance D between the slits is also provided by the manufacturer. The value of L, the slit to screen distance, can be measured with a measuring tape. Pull the measuring tape as tight as possible so it's as horizontal as can be. The values of y and m are determined on the screen. To reduce the effect of error, measure between two bright bands as far apart as possible. The value of y is what you measured, and m represents the number of spacings between the bands that you picked to measure from. For instance, if you pick the fifth antinodal line or fifth maximum on one side of the pattern and the fifth maximum on the other side of the pattern, the number of spacings between those two bands is 10. Now that we've collected our data, it's time to accomplish the purpose, to determine the wavelength of red laser light. And that brings us to our second most common problem that students have with Young's experiment, and it's the problem of units. The wavelength of red light is on the order of 10 to the negative 7th meters. That's a really, really small distance, and a really small unit is more deserving to express it. And that unit is typically the nanometer. We want to find the wavelength of red light in nanometers, where a nanometer is a billionth of a meter. There are 10 to the 9th nanometers in 1 meter. So you can see the issue already. We have one mess of units here. We have a millimeter, a centimeter, and a meter, and we have to calculate the wavelength in nanometers. So if that's an issue for you, I recommend the following. Take all the known information and convert it to meters. Get everything in the same unit first, and then calculate the wavelength of red light in meters. Then convert to nanometers. So I can take my millimeters for D and I can divide by 1,000 to get it in meters. I can take my centimeters for Y and convert it to meters by dividing by 100, and my L is already in meters. I can now use my equation to calculate the wavelength of red light, and the answer will be in units of meters. I plug all my numbers in, I chug out the answer, and I get 6.48 times 10 to the negative 7th meters. But that's not the answer. I need to have it in nanometers, a billionth of a meter. And so I take my answer in nanometers and I multiply by 10 to the 9th, and I end up with 648 nanometers. Let's do one final example, but this time as a physics word problem. We have a lab group doing a lab with a laser and a double slit apparatus projecting the two-point source interference pattern on a whiteboard located 15 meters away. That's the distance from the screen to the slits, and that's L. The distance measured between the central bright and the fourth bright band is 16.21 centimeters. That's the value of y as measured on the screen, the distance between central and fourth antinodal line. So I'm going to use m equal 4 for that. And the slits are separated by 0.250 meters. That's the D millimeters. That's the D value. Now again, you have to give attention to units, so as I recommend, you take everything and get them in the same units. Meters is a good option, so I'm going to take my centimeters and divide by 100 to get to meters. Take my millimeters and divide by 1,000 to get to meters. Now I have everything in units of meters. I take these values and I plug them into Young's equation. I chug out the answer. The answer is in units of meters, since that's how I substituted everything in. To get units of nanometers, I take my 6.75 times 10 to the negative 7th meters, and I multiply by 10 to the 9th, and I get 675 nanometers. It's at this time in every video that I like to help you out with an action plan, a series of next steps for making the learning stick. But before I help you out, could you help us out by giving us a like, subscribing to the channel, or leaving a question or comment in the comment section below. Now for your action plan. Here are 4 resources you'll find on our website. I've left links to each in the description section of this video. The Young's experiment simulation allows you to make measurements and calculate the value of wavelength and get immediate feedback. The calculator pad is a collection of physics word problems where you enter the answer and get immediate feedback and chances for correction. And finally, we have a couple of tutorial pages. Whatever you do, I wish you the best of luck. I'm Mr. H, and I thank you for watching.